we will start. Okay.
Yeah, we can get started.
Okay. I hope our speaker is wake up now. It's a 6, by the way. It's like 7 now. It's just 7 a.m. Okay, so I think today is my great honor to introduce Lily Zhang, from Ford Autonomy. I'm still trying to figure out what's the relationship between Ford Motor Company and the Ford Autonomy. I will ask you guys can ask her later, because we used to be at spending 20 years in Michigan, 15 minutes away from the headquarters of Ford Motor Company. Yeah, but I don't know how the internal structure works. But today we are very happy to have her here, all the way travel from Silicon Valley to come here share with us I think it's a very interesting research, because I know that not just our group, including Dr. Pang's group, also several Xianling's group and Chandra, one of our faculty member. We have several faculty members working in computer vision, robotics at the University of Delaware. We have more than 10 faculty members actively working in this area. So this is going to be a very interesting talk related to perception of how do we deal with this offline, online, etc. I think you already see the flyer. So she right now is a senior machine learning research scientist. Companies keeping coming out the new titles, so we need to be very careful. And then technical project leader, in the autonomy. But the really cool thing is that normally many companies are pretty confidential. You guys know that last Friday we have people come from Uber. Uber come here give a talk about the fleet. But I think when I see online, Lily has been very, that not just working for a company, but also very, I would say, is want to share the stuff. For example, she recently gave a talk at IROS, talking about probably similar topic. But I saw that I originally was planning to fly to Detroit to attend the talk. Then something happened, I couldn't join. Then I told my assistant, so why not we just invite her, come here and give a talk. So that was really, we are very happy to have you here to join us as a UD Mobility Forum. So that without further ado, I will give the podium to you. Thank you.
Yeah. Thank you for the introduction. And I'm very grateful for the invitation to join the discussion today. Maybe some self-introduction first. I usually go by Lily, and I've joined the industry for 5 years so far for automotive and self-driving technologies. The reason why I want to work for self-driving, the reason is very simple, because I want to apply AI research to benefit people's day-to-day life. And I think today's discussion, the main idea is that we want to discuss the online and offline perception system. And I hope that by sharing openly the challenges and the solutions we build in-house, we can inspire more research in autonomous driving and drive those innovations to production, to be commercialized, to be applied for people's day-to-day life. So this is the agenda for the presentation. We'll first cover the Ford L2 Plus ADAS production features. And then we'll talk about the online and offline perception systems to enable the continuous learning loop. And lastly, we will, share what is the main takeaway today. Whenever at any point you need any clarification, you want to ask questions, feel free to interrupt. We can, just dive in some specific point you guys find is interesting. Maybe before we can make this discussion a little bit more interactive.
Sure.
So before we dive in,
ask each of them to introduce themselves. If you want.
Okay, yeah.
Most of them, all of them, except Selena is an undergraduate student working with. She's a junior in our department. Otherwise, probably all of them are PhD students.
Okay, yeah. Yeah. We can do it in a casual style. So before we dive into the slides, I want to ask a very simple question, right? I think everybody here has the interest for doing AI research for self-driving, but how many of you have you ever looked into the user experience and feedback on using the existing self-driving features? The answer might be 0 here. Okay. Yeah.
Actually, when I at Detroit,
Mm-hmm.
we drive a.
It's 3 years ago.
Yeah, 3 years ago, we drive Navia shuttle.
Mhm.
Shuttle. I'm actually was the operator on that shuttle. So that shuttle, from my experience, for the safety, I don't think that can guarantee the safety of the car. That's first the most important thing, because when bicycle drives through the front, so maybe the car will stop very emergent, but it's still very close. It got very close to the bicycle, so that's the very bad experience. And for the comfortness, I think they made a lot of jerk. The car can stop anywhere, and you cannot imagine. For example, if the car see a steep, you know there's a lot of steep
In Detroit, there's a lot of this kind of in the winter, it's being in the middle of the road.
Yeah, so the bus will stop very quick, so you feel not comfortable. If that car designed for old people, I think old people will be thrown out of the car.
Yeah, I think that's a very, very actually interesting feedback. Lots of people talking about how cool self-driving can be, but we neglect a very important fact. There's different machine perception and human perception. The machine feels comfortable to make a certain decision, but human might not feel comfortable with it, right? Building, the self-driving technologies or ADAS system with a consideration of human user experience and feedback is very critical. So for Ford, earlier this year, we released the Ford Blue Cruise 1.2, which is a Ford ADAS system. It has 3 main features released: the lane change assist, the predictive speed assist, and in-lane repositioning. And out of the 3, one of the features is this in-lane repositioning. I have this demo video from a user actually.
In-lane positioning means you're in the lane, but it's just
Adjust the position in the lane.
make sure you're in the middle.
Not all the time in the middle. Maybe let's replay this. Yeah. So you can see this is the first person perspective. The car is in the ego lane and is passing. There's a truck passing, right? And you can see the arrow sign is showing that whenever there's a truck close to the ego lane, the car moved slightly away from the from the center. This is called the in-lane repositioning. This is a very very simple, intuitive adjustment, but it enables this kind of a natural and comfortable, insurance for the users, right? And basically, you can see the sensors included for this feature is this eye tracking sensor, which enables the hands-free driving when you use this feature. For Blue Cruise, for the conditional highway region, you can do hands-free self-driving there. And this is a very simple example to show how do we design a practical ADAS feature. I think right now the Ford Blue Cruise 1.3 is rolling out, which is using this continuous learning loop to improve the user experience with less disengagement. And I think totally it will be 260,000 Ford Blue Cruise equipped vehicles will have this Blue Cruise 1.3 enabled. I want to share briefly about the existing ADAS sensing systems. For the Blue Cruise and GM Super Cruise, they are the levels 2 autonomy systems using camera and radar. And Ultra Cruise, which is also from GM, they are using camera, radar, and LiDAR. For Tesla, they have a very interesting sensor suite. In 2021, they removed the radar, and 2022 they removed the ultrasonics. And recently, there's rumor on the news they are bringing back the radar. And for Waymo and Cruise, they are the main player for L4 plus self-driving. They use the LiDARs as well. And the reason why the self-driving companies, the commercialized, for example, L2 self-driving stacks, they are using camera and radar is because from all the perspectives showing on the right-hand side, from the weather, robustness, illumination, depth information, detection range. Camera plus radar is a very robust fusion approach. And the reason why LiDAR is not commonly used in L2 plus production environment is very simple. It's because it's very expensive. And this is I think a report from TechNavio from 2017. They predict that from 2007 to 2020, the unit cost for the LiDAR VLP16 will drop to $100. This will be great if it is true. But as we are sitting at 2023, almost 2024, each unit cost for VLP16 is still $4,000, right? I think as we are doing perception or AI research for self-driving, there are lots of things other than algorithm we have to take into consideration. For example, the feasibility, obstacle, cost, right? Without further ado, I want to dive into the continuous learning loop, the online and offline perception. I think when we are working in the academia, maybe people don't worry about what is offline, what is online. But when you step into the industry, you realize that all the self-driving companies have this kind of separation. So what is online, offline perception? The online is processing the sensor data in real time, detecting objects, laying signs to understand the environment. It has to be low latency and generalized across all the conditions like rain and snow. It will be consumed by the motion planning downstream task. And in comparison, the offline perception, they are processing the collected data not in real time. For example, if you are working on a temporal model, not only you can use the past and the current frame to build the temporal model, you can also use a future frame because you can use the future data offline. And the goal for offline perception is to build a high fidelity model to label and annotate the large data set. And the idea is to reduce the operational cost. And the goal is to use a complex and computational heavy model without the real-time compute constraints. And they can help validate and improve the online perception system performance. So with these online offline systems, the teams structured in this way to handle the large amount of data sets. And yesterday I was talking with, I think, Xianling, and I realized that we received the new cars from the DD Research Lab.
Yes, we just, I just gave the title on my way.
Yeah. We were just chatting, right? I think for like universities, right, we can actually try to structure the teams in like an offline and online system. So you almost operate like a company. You facilitate the labels on your own without worrying about paying a huge bill to do manual annotation. And I will talk more about how we can approach to auto annotation in the later slides. Okay, go ahead. Yeah.
So I work in the field of vision recognition. I feel we might have a different definition about perception. In your definition of what you mean by perception, in our definition is more of knowing the environment and interact with the environment, and also do the estimation. Maybe that's my definition of perception, but you might have a broader way of defining perception.
I think my definition is how you enable the car to see the environment. And for example, for Ford, we structure in this way, right? We have the perception team producing the objects detection signs and the lanes, etc. And they will then pass it to mapping and the motion planning team. They will consume these the environments we perceived and do interaction planning. Maybe
You know the environment is the perception.
Yeah. So if we take the online offline perception into the context of this continuous learning loop, and we can start from the driving data. The driving data came from a different sensor suite. The camera and radar can be consumed by the online system, and additionally, you can leverage LiDAR to build a heavier model for offline perception systems. And for the offline perception systems, you can do anything you want, basically. You can use it to do scene understanding. You can use it to identify difficult scenarios, the edge cases, or whenever it fails. You can also build a very strong model to do auto annotation using generative AI to do data augmentation. Along with the manual annotation, you can expand the training and validation data set to retrain the model, to bootstrap the model, to improve the model performance with the target domain. And then you do extensive evaluation testing before deploying the model to the edge devices. And then whenever you reach the standard to deployment, for deployment, you can apply the online model for real-time driving. And when the online model applied to the real-time driving, you will identify more edge cases, more failure modes. You take that into consideration to this loop. And iteratively, the online and offline system can bootstrap each other with more and more data involved. So I will break this continuous learning loop in each component to share what we have done, at Ford. So the first thing is the 3D perception. So when we think about deep learning, machine learning for perception, there are many things we can do, right? Segmentation, occupancy prediction, object detection. Like if you think about what is the most important thing, you want to think about it from a safety perspective, right? For obstacle avoidance, which is a top priority for self-driving. So the most important thing is actually to do 3D object detection, to sense where exactly the obstacle is with position, shape, dimension. So for the 3D perception at Ford, I cannot share with you guys exactly the architecture we've used, but I can share with you what we have been taking inspiration from, which is the bad fusion and bad verse algorithm. So for bad fusion, it consumes the multi-view camera images and also the LiDAR sweeps and passes through the encoder and then project these camera feature and LiDAR features to the BAV space and use a BAV encoder to do the feature alignment. Then following with downstream tasks such as semantic segmentation and 3D object detection. And for bad verse, there's one thing differently. It's taking more, bad verse, the architecture designed to handle different lengths of the context window. Not only you can use like a 0.5 seconds short context window, but you can also use like 1.5 seconds or 3 or 5 seconds. It's enabled by using a spatial temporal encoder. And then after that, you have these multitask detection, motion prediction, and the semantic segmentation. The detection and the segmentation are similar to the bad fusion. The motion prediction is a little bit different. It takes the past 2 seconds, predict the future 5 seconds object trajectory. For the 3D perception algorithm, it won't be possible without the novel and the impactful data sets. And from the past year, actually, I've seen lots of interesting data sets released. One of them, I think we've also been using that internally, is the ZOD data set. The interesting fact, and I want to highlight here, is that previously we've seen lots of leaderboard, nuisance or Waymo state of art, right? But for nuisance and Waymo, they are all the urban driving thing. The range they care about is only 50 meters. But for L2+, we care about highway, high-speed driving. If you drive in 70 miles per hour, you need to make sure you have robust perception for 200 meters. So going from a 50 meters detection range, 200-meter range is actually extremely difficult. Life can be even more difficult without the proper data. So I was actually very happy that, for example, ZOD got released because they are actually the only one data set with 200 meters good annotation.
So who is the entity behind the CDP? I saw the post on the video. I think I also asked here to look at. Is this one free for us to use?
It is free. Yeah.
Free.
Yeah.
And we can use this to publish papers.
Exactly.
We probably cannot use this for commercial. But anyway, that's not our focus.
Yeah, I think I took a look on the license. It might be also free for the commercial usage.
Who is behind it?
This is enabled by the company called Zhang. They are a startup company in Europe.
Okay, there's another one. There's another one from Cognata.
Cognata.
Yeah, Cognata, right? Cognata is also the data the company.
Is that the simulation company?
It's a simulation.
Yeah.
But they also use the data from Google.
Okay. Yeah. Yeah, I used to work with Cognata on like a POC. But for this data set, I think I encourage everybody to use it, to publish it. If you take a look on their GitHub, the SDK is also very well built. It's very easy to follow. For whoever used to work with Nuisance, they built their framework very similar to Nuisance. It's very easy for us to adapt. In fact, if you train today with a ZOD data set, you can evaluate directly using the Nuisance metrics without too much without too much adjustment. So, and it's just got released fresh out of oven from ICCV 2023, like a month ago. So I think this is a very good data set. You can do like single frame LiDAR detection. You can also do temporal. The temporal data set is smaller. The independent frames data set is bigger. But the key thing is the 200 meters annotation. And in addition, apart from objects, the lane is also very critical. So this is a new data set called OpenLane V2. They have the 3D lane annotation. On top of that, there's also this data set called AutoLights. The interesting thing about this one is that they have very practical sensor setup. They have the short range camera, which is 30 meters with relatively wide field of view, and the long range camera with 64 meters. This is similar like what we do at in-house as well. So I think we've seen more and more interesting data set, and the researchers taking consideration about what does the production need, right? I think it's good to contribute, you know, when they're at a very early stage. Yeah. Oh, go ahead.
So what's the main reason that's really the I think we do the meeting time just need to be like
Oh, okay. Maybe different self-driving system consume things differently. For example, for Ford, we do need the 3D lane prediction. And as I mentioned in the previous slide, we do the 3D object detection and 3D lane detection. Yeah.
So this means your track. That's why it's good. I know it's a thing that we finally doing. Why we do this way, but I really love this when you're also becoming very cosmic. Seems like a very yeah. But that's good to know because wow,
yeah. I think the benefit is that when you have the 3D lane detected directly, right, you don't have to do any kind of projection from 2D to 3D space. But again, I think this is what we approach the problem. So I want to share briefly about how can you approach a 3D object detection. So recently I came across this paper, and it's very similar and relevant to what we've been doing in-house. So I think the idea is that you can take a single keyframe LiDAR to do the framework consumes a different detector. For example, the detector can be trained with Nuisance and also trained with another detector trained with Waymo. Because different detectors consume different data sets, they complement each other. You don't want to only rely on one detector to annotate the data, but you rely on multiple detectors to, you know, consume the domain knowledge from different data sets. For example, if you use a single frame LiDAR object detection, it will work good for detecting objects generally. But if you use a multi-frame, a longer context window object detector, you can detect the static objects much better. Because when you do the temporal accumulation, the static objects will get much denser point cloud, right? That's why you get better performance. The idea is to leverage all the different detectors with different advantages, and then do a fusion on detection using tracker to serve as a state classifier if it is static or dynamic. If it is dynamic, then you use the pedestrian tracks. Then after you get the pseudo labels, you basically using NMS to select the best centroid, the dimension, the objects, and then you get the pseudo labels. for the first round of pseudo labels, maybe it's not ideal, but iteratively going through this process basically is a self-training procedure to improve the pseudo labels. If you do it in a nice way, you can actually achieve pretty similar results as supervised learning. This is actually a very economical friendly way to do annotation. And the code is also open sourced. Yeah, so feel free to take a look. And on top of that, I want to also share with you some of the data algorithm we've developed in-house. So the idea is that when you train a model with nuisance, you don't need to worry about the volume of the data set. You will never run into out of memory issue. But when you train with a large amount of data set, memory, the GPU cost and everything will become a top priority. Instead of working with a fixed data set, you work with a dynamic evolving data set. Then you want to figure it out between this batch of the data set and the next batch of the data set, what's the similarity? How can I reduce the redundancy? Because if you just train a model with redundant data, you will actually hurt the model performance. It's not train more data set, the model will be performed. It's more about training with the right data set. So this is how a comparison we have. When you work as a PhD in academia, you can maybe you think more about model and algorithm development. You think less about data set, right? But when you work in the industry, most of the sleep was lost on worrying about data problems. But the data is a food for cooking good AI recipes. So I actually encourage everybody to look into more on the data problem, because once you solve the data problem, you also can solve the scalability problem. So in terms of data algorithm we develop in-house, the first thing is about scene understanding. And this is from our CVPR paper, which we developed a deep perceptual image clustering framework. It's a multi-stage approach, because after the stage 1 clustering, we use like a set of data set. For example, as shown on the screen, this is the parking lot data set. You pass it through a feature extractor. You can use VGG16 or CLIP. Then you do dimension reduction using PackMap and DB-scan for clustering. You get the first stage clustering. You can see that the objects and the image with perceptual similarity, they will be automatically grouped together. But with only one stage clustering, the information, the meta information you get is very coarse. You want to get more refined details, because ultimately you want to get very niched clustering. Then you can attach meta labels to that category to do some kind of meta annotation. So we dive deeper. For example, taking one cluster, you apply the stage 2 clustering. We realized that after a second stage clustering, you can get a more niched result. And this framework is super helpful because you can identify dataset bias in the unstructured and unlabeled data. For the downstream tasks, you can do meta annotation, finding incorrect labels, edge cases, mining for similar images. And on top of that, recently we also explored using multimodal approach using CLIP. For example, you can pass a language query driving a scene with crosswalk at daytime. If you feed it through the database, you can retrieve the corresponding data. So I think the example shown here is how can we curate and understand the data set efficiently. And I want to show a very interesting example on BDD100K. So BDD100 has been commonly used in academia, but I think people really think about what can be wrong with the data set. This is a stage 1 DPIC clustering result. It's separated into 2 big clusters, the day and night. If we overlay the cluster with the meta information from BDD100K, we find that around the red clusters, there are some orange dots. The red cluster representing the night data, and the orange one represent the daytime. In comparison, the same thing when you look at the day cluster, which is majority daytime data points, but you can still see some red night images, data points there. This doesn't make any sense, because the whole point about doing perceptual similarities, you want to have ideally the image with similar perceptual features will be grouped together, right? How could the night data be mingled with daytime clusters? And we dive deeper and find that those night labels, in fact, incorrectly labeled as day. human mistakes are inevitable. So with this kind of frame, and the same thing, when we look at the data points, we find that those the points clustered as the day, they are in fact some very edge cases. For example, this one, the orange dots in the night clusters, which labeled as day, but they are very similar to night because they are under the bridge, they have the overexposure edge cases. So these are all like interesting thing and correction you can do with the framework we've developed in-house. And I want to also share another approach we have been developing for data augmentation. The key idea is to focus on the bias in the context of noise distribution for task-specific noise factors. So, for example, for lane detection, you want to consider the name of the lanes in the scene, the lane marker types and the condition, the weather and lighting effects. If you want to achieve this kind of diversity in real data is very costly. So we developed this two-stage synthetic data augmentation approach. First, using simulation to create a synthetic data. The idea about simulation, you can get unlimited free labels. It's a known fact. We started to do this about 5 years ago. And then you pass it through unsupervised sim to real translation to get more realism on the simulation data. Because the nice thing about unsupervised that you don't need to have any supervision, you don't need the labels, but because we control the receptive field precisely, that even with the translation, it won't change the objects in the scene. As a result, you can reuse the labels from the simulation, but with enhanced realism. And then we fed these sim to real translate data to perception task. And I want to show you some of the features developed in-house benefited by this two-stage approach. First is the parking lot detection, then is the lane detection, the third one is monocular depth estimation. We did a very extensive studies. Feel free to check out the CVPR paper as well. All these three tasks, they have been improved using a combination of real and sim to real data. I want to show you the challenges here. So for parking lot A is collected in Dearborn. It's a sunny day scene in Dearborn, and parking lot B is in Palo Alto, the GFL lab. If you train a model trained with parking lot A, it can perform very well on the parking lot A dataset with F measure of 91.4. But if you apply the same model to parking lot B, it actually achieved a 0 F score. This is pretty painful because when you deploy a model trained with a limited domain dataset, but do a different domain, it will completely fail. It's very miserable because it's a safety concern. That's why we want to look into the domain adaptation problem, addressing that by a sim to real translation approach. This approach is a data-driven solution, and using a combination of GANs and 3D engine, we've observed consistent improvements for all the three tasks for parking lot, highway lane, molecular depth estimation. So yesterday, I think I adjusted the slide a little bit to dive into about the technical details. Feel free to ask any questions. So I think when we work on AI research, you always want to do something novel, right? How did you come up with a novel idea is very, very good thing to think about. For me, at least for my team, I think for working for production, for the past 3.5 years, I've been working on the RNA research, right? And from the past 1 year, I've been focusing on the production. So in the industry, you often encounter lots of restrictions, the cost, the volume, the data, the funding, and everything. But often you can actually turn the restriction to research opportunity, because when you're facing the challenges, right, the impossible mission, you can either turn around to go with a different direction, or you push it through. And I want to share with you one example how we solve the restriction and turn it as a research opportunity. So this is auto hitch. For Ford, one of the most important model is a pickup truck, the Ford F-150. And one important feature is to do hitching. When you back the truck, you want to hitch precisely with the trailer. So the idea is that the vision algorithm should detect the center of the hitch ball precisely to assist the hitching behavior. But when we find there are some failure cases. For example, before the shadow covered the hitch ball, you can see the detection on the hitch ball is very precise. But for this next frame, when the shadow covers hitch ball, because of this perturbation, the hitch ball center is no longer detected properly, detected further because of the shadow existence. From these cases, we identify shadow is a very strong disturbing factor, but it's very expensive to collect all the different times of the day. So the problem becomes, how can we generate the shadow data? We can generate it from simulation data, but the simulation data plus scan approach has restriction. It's not physically consistent. It can be random from time to time. What we want to approach is a physical consistent geometry aware relighting method to generate a shadow that's consistent with the vehicle geometry. That's why we considered this approach. And we did lots of literature review. The previous relighting method, they usually rely on multi-view datasets, as shown on the left. The input views can be from different cameras to do the 3D mesh reconstruction. But most of the self-driving data set we have today is a single view. Basically, you have the camera mounted, then you drive with the camera through the thing, right? You have only one viewpoint to see the environment. You cannot drive the car, rotate around an environment to get a multi-view data set. So ideally, you want to have this kind of multi-view set up, but it's very expensive and it's unrealistic to set up to collect a large amount of AV data sets for the 360 view. And the first iteration we have is a multi-view approach. So we basically take the existing multi-view relighting method and push it through to make sure that it can work with some kind of single view data set. The idea is that we take the single view kitty sequence, pass it through the detectron to do semantic segmentation. And the reason why we want to do this semantic segmentation is because the sky can be a confounding factor when you do the mesh reconstruction. We want to remove the sky or other confounding factor. So then you take this processed frame to do COMAP based structure from motion and multi-view stereo to construct a dense point cloud. Then you use a Poisson surface reconstruction to get the mesh. With the mesh, you can derive the lighting illumination buffers, like the norms and also the reflectance map. Then you pass it through the relighting network to get the relighting result. This first iteration works okay. For example, you can see with the sky segmentation, we remove these noisy mesh that can help get a clean relighting results. But it has many issues. For example, we applied it to kitty. There's 11 out of 21 sequences failed. When the driving scenes with insufficient feature matching, it will usually result in the failed mesh reconstruction. It's also very heavy compute. Usually take about 5 to 10 hours for one sequence to converge, which is only 200 frames. It's not very efficient. And all of these concerns brings this to be a very restrictive application. So we come with a second iteration. Basically, the issue is that we lack multi-view data set. We can solve it by two approaches. One, we go out spending more money to collect multi-view data set, which is not very sustainable because it's expensive and hard to achieve. The second approach we can have is just to replace the multi-view restriction to be a single view approach. And this is now our CVPR paper. It's also presented in the GTC this year. The idea is that instead of using a multi-view data set, we only take a single frame and pass it through the molecular depth estimation to get the predicted depth map. And then instead of using the COMAP to do the mesh reconstruction, we warp the sheet based on the predicted depths shown as here. And then you derive the illumination buffers like the reflectance map and normal maps. For the second module is the image relighting. With the known input lighting conditions and the target lighting condition depends on what the user wants. If you want a 5 p.m. or 6 p.m. afternoon or morning lighting condition, we have these source and shadow map refined through the relighting network. The relighting network is basically ResNet based. And then you pass it through the final relighting refinement network to get the relighting results. And I want to show you guys some results for Simba. Basically, the input is a single frame. You can get the 3D scene mesh, and then this is the relighting results, which is concatenated using 120 relighting results. And you can see, okay, maybe we can play it again. Yeah. So the idea is that we want to have this kind of controllability on, relighting the shadow only as the only varying factor.
Is this one already open source?
This project is not released yet, but I will talk about another project which is open sourced.
Okay.
Yeah.
This is cool. Yeah.
Okay.
He will come to you separately.
Okay. Yeah. So basically you have this input frame and you have the augmented data with the shadow, right? With different novel shadows. And this is very efficient because you don't need to go out, spend one day to collect different shadow. You can just click a button. Within 5 seconds, you get all the shadow related results. And I think we released this data set. So this is, we call it Simba in the wild, because basically you take any input frame, you can relate any kind of architectural driving scenarios. This is from the Dev2K internet images. We do find that if this is a high resolution data set, the Simba achieve much better results. And I want to highlight the most important component of Simba. It's not about getting a fancy, interesting relighting results, about how we can use it to do data augmentation. So for center track, it's one of the state-of-art simultaneously object detection and tracking algorithm. The experiment setup we have here is that for the kitty tracking data set, we have the 21 sequences of the noon driving scenarios has 8,000 frames. And for the train set augmentation, we apply Simba to generate 4 different lighting conditions, the 4,000 frames, and also using the improved baseline we've developed as a comparison. For the test set, we use Virtual Kitty. Virtual Kitty is the exact clone of Kitty, but it has morning and sunset and different lighting condition as 4,000 frames. The idea is that we use the Kitty training set, which is noon, and also reuse the ground truth, because for Simba, we just change the lighting without changing the position of the objects. It's geometry consistent. So you can reuse the ground truth. You combine the original Kitty noon and 4 different variation of relighting result. You pass it through center track, test it through Virtual Kitty. So the idea is that the baseline approach will be noon only. When you test it on Virtual Kitty, it will of course fail, right? Because the unseen lighting condition. But with the Simba augmented approach, we expect the model performance has boost. And this is the result we have. So for K is the baseline without any augmentation. We use the matrix MOTA, MOP, the multi-object tracking and precision accuracy. MODP is a multi-object detection precision. So the model K is without any augmentation. Model K plus M is the baseline improved with MVR approach. And the K plus S is Simba. And we can see there is a very big margin of improvements comparing to the baseline. Overall, I think there's we didn't run the training for only one time, but repeated it for 5 times. And consistently, the K plus S model achieved the best overall performance. And we have a qualitative comparison side by side here. The top one is model K, middle is the model K plus M, and last one is the model K plus S. Okay, I think maybe I prepared too much materials. So if you guys have any questions, okay. Yeah. So I think the idea I want to share here is that how can you make novel contribution? You identify the problem, right, through work or research. For example, shadow is a problem. You come up with a generative AI or AI approach to generate the data to solve the problem, and you validate the problem solving is valuable, is impactful by performing a downstream task. And lots of times when we review the paper, they usually get only on stage 2, right? They produce some results, but they don't do downstream evaluation. I think the downstream evaluation to show how useful it is on the downstream task is actually the most critical. In this case, the center track model trained with Simba augmentation achieved the best result at unseen lighting and shadow perturbations. Lastly, I want to share an online approach we've developed in-house, and it's also open sourced. So for online perception, there are many things we need to worry about. The compute, how do you do edge deployment? It's also very important to make sure the online algorithm is generalizable, is reliable across different domains. There are many ways you can approach to build a robust, generalizable online model. I want to share one of the approach we've done recently in ICCV 2023. So shown for this architecture on the left, which is the current method, basically you need to rely on the ground truth to understand the data distributions. And on the right is our approach called data equity, which is only relying on the perceptual likelihood. To some extent, it's kind of an extension of the deep pick framework we built, but taking it further. What we have here is that we have the input data passes through the feature extraction and using the last layer to do clustering, and then use the perceptual similarity to build this sample likelihood info bank, and then build these data equity weights. The weight function is eta. The eta is the likelihood of sample occurring in the data set, and the gamma is the hyperparameter. The eta and gamma are the hyperparameter that control the shape of the weighting function. The p is the likelihood. And then basically you can train with these generalized focal laws we developed and compare with traditional training without any generalized focal laws. And we've seen the downstream tasks improve, especially at, for example, objects like a van or a bicyclist. And the code is open sourced. We encourage everybody to contribute. And feel free to let me know if you have any questions running the model. We applied the same generalized focal laws to different 3D object detection tasks, including DD3D, Batformer, Batfusion, all the state of art. So just to break it down, right? The idea is very intuitive and simple. The figure here shows the Kitty and nuisance data set. You can see without relying on any manual annotations, you can see the groups of different data, right? Using the perceptual similarity. And then you basically do DB scan to get the clustering. The sample likelihood calculation is super simple. Basically, it's the number of the samples in the cluster divided by the total samples in the training set. That's what we call sample likelihood. And this is the evaluation results. We evaluated on Kitty, which you see, it has 9.75 improvements over the baseline. And when we evaluated on the Kitty test set, we observed a very interesting trend, which is going from car, pedestrian to cyclist, going from easy to hard object category. The data equity loss, the generalized focal loss assisted the DD3D model actually perform much better when the tasks get harder. We also applied that on the nuisance data set with a different architectural Batfusion using the camera-only approach. We've seen 10% improvements over the baseline for NDS. NDS is like a combination of all the metrics here. So I think that brings us to the closing remark. When we work in the industry, right, I think it's very interesting that we've have the access to get the first-hand problems. We identify the challenges in the AV deployment. And I think for people working in the research, it's very important for the research to align with industry needs. because then you can really bring impactful work, right? And then as I presented, we discussed today, there's the online and offline systems, the online perception, offline perception. I think not only the industry, can use this kind of a structure, but also academia can do something similar, so that there is a smooth transition if you go from research to production. Especially for the offline perception part, you don't have to worry too much about the compute restriction. You have more freedom to do research. But I think the edge ML is also a very critical part that worth more investigation. Lastly, I think the reason why we want to do this kind of online offline tailoring is because we want to enable the continuous learning loop and iteration. Yeah, that brings to the end of the presentation, and I'm happy to take any questions now. Yeah.
So we still have time. Any
Okay.
Yeah, I think the talk is very interesting and informative.
Thank you.
I have several questions. I will be quick. So the first question is about related to your title. So I was curious about when you say online and offline, you actually do prediction and collecting data in online stage, or you doing the training part in offline stage, or you can also do the training in the online stage.
Yeah, that's a very good question. I want to clarify. So the data collection, so there's data collection team dedicated for data collection. When we receive a tons of the data on a daily basis, the first thing we do is to run offline perception to do auto annotation. We run this kind of iteratively, right, to improve the pseudo labels. And because you run a software, will be much faster than manual annotation. Then the pseudo labels will be passed to the online team to train their model. Because for the offline team, we build a very heavy, accurate model. The labels is relatively accurate and it's large amount. And then the online team will get the first round of the training using the pseudo labels, right? And maybe like a week later, the manual annotation will come. Then they can train it. We can bootstrap the pseudo label with the manual labels, and the online team will also get much accurate labels. So for training, both offline and online they train, but it's a slightly different stack. For example, for offline, it's supposed to be this kind of complicated model, but the online team will be relatively simple and efficient model, but they both train models. Yeah.
So for the online model, does it train the embedded system on the car, or it train actually in the server?
So right now what we have is that you can train the online model on the cloud, right? Ford has our internal clusters. But when we deploy, for example, as I mentioned in the Ford Bluetooth 1.3, the idea is that we deploy the model on the car, but also receive the real-time feedback and do some adjustment. But it's not released yet. So you can, ideally, you want to do it both way. Yeah.
Thank you. The second question is about the DB-scan clustering. So I'm curious about, so after the DB-scan clustering, does it come with the label automatically, or you need to label in the manually or something?
Yeah. So for the DB scan, what it does, it has, it cluster, group the data points together, right? It won't come with any labels. So you will need to bring human in the loop to attach pseudo labels. The idea is that if, for example, the one cluster have all the crosswalk grouped, right? The human will understand, okay, this is a crosswalk. You can't have human in the loop to do it. You can also have a different detector to do it. But for DB scan, it won't come up with any labels. It's only a clustering approach. Yeah.
Okay.
Yeah.
One last question. What happened about that cage at the for the current stage? I mean, you need to use for example, a truck driver need to back up and cage the cage.
Okay.
So what's the result of that problem? So have you solved that?
So yeah, basically, what we've have here is for example, for the vision system, the reason why it failed previously is because it hasn't seen any shadow data, right? So using a combination of data augmentation, if you train a model with more shadow variation, it will need to understand, even with this kind of shadow perturbation, it will able to achieve accurate performance. That's the idea. Yeah.
Thank you.
Yeah.
So if follow up on the shadow prediction, was there attempts to combine the prediction and fuse it with the, for example, the IMU sensor on the vehicle, so that with sensor fusion, you'll be able to more accurately detect the images? Instead of just solely relying on the camera, which will have a mass impact when there's the shadow present.
Yeah, so that's a good question. So for Ford, the ADAS L2 system, we use a combination of camera and radar. For the auto hitch system, I think it's camera only vision system. I'm not sure if they are doing any sensor fusion there. Yeah, but it's a good point. Yeah.
How do you develop a model for the shadow? Do you actually use it streamline in the preparation for the offline brain data? So did you include that model on the real world, or is it still in like a research phase or a conference?
Oh, okay. Yeah. So the reason why we do research is to apply it for production. For example, for auto hitch, right? It's a very important feature deployed on the F-150, which is the most important vehicle, one of the most important vehicle at Ford. In order to make it the vision system to be robust, we did use the synthetic data augmentation using, for example, the GAN, the simulation approach. So it's definitely applied for production. Yeah.
Do you measure the impact of the sort of processing? It's not reference necessarily, but do you measure the impact of the research you do? There's a cost, and then there's supposed to be a benefit.
Yeah. I attempted to do that by inserting in the slide for example, for Ford Blue Cruise, it has 2,600 users, right? I don't have the exact number on how much revenue I have contributed, but I think I feel very happy and thankful that I have the opportunity to contribute to the feature going to commercialize the vehicle. Yeah.
I was just asking to understand if it's like a streamlined process, so
yeah. Yeah, I don't have the exact number out of my mind. Even I have it, I cannot share it. So, yeah. Okay. Yeah. So I think Tesla did release some numbers in terms of how much they earn for each customer, using their autopilot system. It's similar concept, right? Ford is trying to push the more advanced Blue Cruise feature. Right now, the unit cost is relatively expensive. But with more and more users using the features, we will get more impact and resources allocated to develop it. I'm pretty sure in the near future, we will have more impact and revenue, from the ADAS systems. Yeah.
Thank you for I have a question for the family.
The what? Oh, okay.
Yeah. So currently doing two brands, right? We consider like any modality one. For say you have for some image, you won't have the RGB and without the layer and then.
Yeah, I was actually thinking about talking about it. So right now for Ford, the feature deployed in the vehicle, we use camera plus radar internally, right? So for Battle Fusion, it uses camera plus LiDAR. We mainly use camera plus LiDAR, for example, for offline model development. And I think, is that your question about how do you do this kind of cross-modality adaptation?
It's not adaptive. Will you have those sort of data in computing How do you build it for, how do you use it in the model?
Oh, okay. So for example, I have encountered the issue of the missing modality data. But I think I was actually thinking about a knowledge distillation approach. So basically, we haven't tried that yet, but the idea is that if you train for example, camera LiDAR model, you teach the model to learn how to do depth prediction using the knowledge, the feature from the LiDAR. But at the training time, that's at the training time. At the test time, if you have only camera data, because you don't do this kind of direct supervision, you do implicit supervision, then you don't have to have the LiDAR modality. You can have a camera only to do it. I think there's a recent IROS paper I was thinking about to share with everybody, but I think we're running out of time. This is doing exactly what I just mentioned. Basically, it has this teacher model, which is trained with LiDAR feature, and there's also this student model that trained with camera only, but learn the teacher features. And then using the adversary laws, you can try to reduce the domain shift between with LiDAR or without LiDAR. But we haven't, I think for your question, it's a little bit different. I don't have an answer on top of my mind right now, but we can discuss more about it offline. Yeah. Yeah.
So for the shadow project, I was just curious to know, like, we also try everything light source and reducing the shadow.
The light source?
Yeah, have some lights which can focus on the ball and reduce the shadow.
To reduce the shadow. So the light source, we have two light sources. One is the sky, the other is the sun. So basically, when we do relighting, there will be a sky model and the sun model. Based on the input lighting condition, you will adjust the sun and the sky model parameters and producing different shadows. But for your question, I think it's about the intensity of the light source, right?
Natural lights, I don't know, the man-made lights. I think the light source is
For men, okay. We haven't tried that, but the thing is that when we train the relighting network, it's completely using simulation data. So it's actually simulated. It's also man-made. Yeah. Yeah. In the simulation, you have the sky and the sun model.
So the ground truth for the shadow, auto shadowing is, the ground truth is from the simulation.
Yeah, it's purely synthetic data. Yeah. Yeah.
And a question about the simulation. So were there any attempts to combine synthetic data with a digital twin? Because while in Michigan, driving on the highway, I often see the Ford vehicles collecting data on the highway. So was there any attempt to reconstruct the digital twin of the Dearborn and the highway area and combine that with the data generation?
Yeah, I think I've seen some research done that before. The idea is that you can get some real data from digital twin, and then you have more variation from the simulation data. Ideally, you want to have this perfect balance between the bias, which is the target real data, and the diversity from the simulation, right? I think that's the best approach to do. That's also what we did in the synthetic data augmentation paper. Yeah, so that's exactly what we did. Yeah. Move down.
Thank you.
Yeah.
Do we have any questions online? The ones people online, ask them, type of question, or they can unmute themselves, ask about it.
Yeah.
So while we're waiting here, I want to answer your question, just give me I also know the director for the super group, when the PhDs are our department, this department, the advisory council, he was here in May. So he's leading the super groups, you guys will group that. So Yeah, very interesting, very different, although for GM, it's, the company is very close to the, used to be. But when we invite GM folks coming here, with us, they barely talk anything about the okay, that's understandable. And then I probably, you guys are very interesting. For example, you probably know, much more in the latest research in this field. I don't speak for them. I said, okay, so, ICCB, and all the things. So I'm just curious about the culture, for the autonomy. And so you guys really looking for the, you mentioned the blue post, you mentioned the blue papers, it was just published, like,
Bevers and Bev
yeah,
Fusion.
is this growth, does that come from your group?
No, the Bev Fusion and Bevers paper, they are, Bev Fusion is from MIT.
Yeah.
And Bevers is from another person, I forgot the research lab. So I didn't share the exactly architecture we've been doing, but I want to share with you guys some paper we have been inspired. Yeah.
So that's, I feel like you guys are doing applying this latest, research, research. But it is, I can tell from your presentation, expert, and then learn from the latest one, even contributed to the community, and then apply to the product. This completely changed my view before, because I always feel like for the company who do the production system, they probably don't really look at what's the latest research. I'm just this before.
Yeah.
Say it's not a question at all. It's just my observation. But when you also good friend, so that when we come here, he said, I can't talk anything about it when I'm doing it. So I can tell you something I did about PhD at CMU. Wow, that's about almost 20 years ago, right? So it's very different. I can feel it's, the culture here. But do you feel like but yeah, I don't know. I don't have a question here. I'm just saying my opinion.
Okay.
This is really good. Because I also like the way, probably because you have been leading the university for a while. So you can share the experience, how you identify the problem. That's aligned very well with what in my lab. I keep telling them that don't just read a paper find a problem. You always need to looking for the real, like using the F-150. He had the F-150. That's why he care about this.
Oh,
So you're gonna tour a boat, right? So ideally, automatically, that would be nice. This is a real problem, and how this is going to be done back to your research. So I think this is great. Yeah.
Yeah, thank you. I think whatever I shared today is published results.
Yeah.
So and I also want to share some perspective from the industry, right? Because I hope I didn't release any confidential information. Yeah.
You guys right? So
yeah.
Comments come from MIT, CMU, but we sense that this is actually changing. We have been working with many of you see this afternoon you're going to see that, for example, we do, but sometimes I feel like not all the companies do this way, especially for the production team.
Yeah.
Probably don't look at the necessary, look at I think it's a mindset. It's because your office is in California. If you are fortunately in Michigan, you probably will not be as you are today.
Yeah. So for the past 3.5 years, I've been working in the research, right? And then recently I shifted the focus to working in the production team. Lots of the work I presented today is from the research time. And it's, when you work on production feature, the deployment, the production become the top priority.
Yeah.
So you no longer have that luxury time to do novel research. So I do see the difference between doing research and production. But the very ideal case is that we don't want to work with out of the stage software stack. We want to, align the research need with the production demand, right? So yeah, that's what we have. Yeah.
Because I think that you guys probably see, we invite a lot of people come here to visit us, so you can see that from California and from just the mindset is different. That's great.
Yeah.
Do you have any question online? No. That's fine.
Is there any leading relationship between the product team and research team? For example, if I'm doing product, how do I define the needs for the model? I need to figure out which model fits the car best, or just research team can tell me. I just follow the research team and do simplification of that model.
So right now, for self-driving ADAS related work, there's no research team. We combine into one production team. So it used to be the research team developed the algorithm. We had a handover to the production, they deploy it, but it's no longer the case. The team merged into one. So there's no longer this kind of communication. There's no longer this type of handover, just one team work on the same thing. Yeah.
So how are you reading the paper? Is that doing a paper presentation in a group, or everybody can read paper and share?
Yeah, so I've been leading the paper studying group for 5 years now. What we're doing in-house is that, for example, IROS, right? I was attending IROS to give a talk, and I find lots of paper which is very relevant and interesting. Basically, a few of us, we will work together to set a list of topic, Edge ML, 3D perception, domain adaptation, and to find the best paper from IROS. And then for each topic, one of us will lead a discussion, review the paper, and present it to all the people in the autonomy team. And that's what we've been doing from the past 5 years. Yeah.
Maybe you can tell us from your team's point of view, what are the top conferences you are looking for? So I see ICCV, listed CVPR, NEWS, IROS, ICRA, anything else? Because there's so many papers. While you're talking here, probably already 10 more papers published.
Yeah.
So it's very difficult to tracking all those papers. So how do you?
Yeah, I think paper reading is a lot of work for me on a daily basis. So for me, because I work on perception, I think I read most of the paper from, or publish the paper from CVPR, ICCV, ECCV, NeurOps. For people work on, for example, motion planning or mapping or other field, they would be a different focus, right? So what we're doing is that we have like the host from each pillar, perception mapping, to lead the discussion. For them, I will be in charge of getting lots of the machine learning perception paper, right? Other people will do different paper curation. So and I also think the venue doesn't matter this much now. For example, recently there's a paper from Huawei, the company did a paper called Label Former. It's also a very interesting paper. They didn't publish anywhere. They just put it on archive. Same thing for Bioverse. It just open source the data, open source the code without worrying about publishing anywhere. I think publishing the paper at the HOP conference does add more credibility for the work, but it's not the most important thing. I think the open source thing is the most important thing. That's why I want to always contribute to some open source project. And finally, this year we had one project open source, the data equity generalized focal loss project. Yeah. So hopefully people can take a look and contribute as well. Yeah. Yeah, it's open source. Yeah.
Okay. Do we have any questions from the audience? No, thanks our speaker one more time.
Thank you.
So I will bring it back to you.